So we are in BEA5 again. It's the second instruction video. I'm going to explain you some things about filtering. Now, the essence of a filter is that you send a signal to the filter. It takes something out of the signal that you send in, and the rest is passed to the output of the filter. Just like a filter in a coffee machine, there's something inside the filter, and only part of what is inside comes out. Now, to explain the effect of a filter on an audio signal, it is convenient to draw a diagram. And in this diagram I'm going to show simplified effects of the filter on the sound. So now I draw something like this, where the horizontal line represents the frequency, with, let's say, the lowest frequencies that we deal with in audio are around 20 Hz, and the highest frequencies more or less 20 kHz. And then 1 kHz is somewhere in the middle. Now, why is 1 kHz in the middle? It is of course not half of 20 kHz, but exponentially it is. When we are talking about filters, we talk about intervals, just like when we are sitting behind the piano. So going from 1 kHz to 2 kHz is an octave, just like going from one C to the next C. And then if you go from that C to the next C, you again double the frequency. So from 2 to 4 kHz is the same distance perceptually as going from 1 kHz to 2 kHz, whereas the frequency range is doubled. So this is why 1 kHz is more or less in the middle. So 1 octave up is 2 kHz, 2 octaves up is 4 kHz, another octave up is 8 kHz, and another octave up is 16 kHz. And going down is 500 Hz, 250, 125, 63. Okay, now if I have a filter where the frequency characteristic is a straight line, let's do it like this for now. That would be a filter that doesn't change anything to the sound. Unless this whole line is a little bit lower or higher, it would change the overall level of the sound, but it doesn't change the frequency characteristic of the sound. But as soon as this line has some kind of curvature, it changes the frequencies in a certain range in relation to the others. Now, one typical type of filter is a filter where you have a straight line here and then you go down. This is called a low-pass filter, or LPF. Why is that? Because the lower part of the sound is passed through the filter, whereas the higher part is taken away. You see that I did not draw a straight line here, but I draw a curve. And this is because a normal filter, I mean, in digital technology there are existing things like brick wall filters, which is indeed a filter where there is a straight line, but in an analog situation you will never see that. In an analog situation, a filter always has this kind of characteristic. And this slope that you see here is called the roll-off of the filter. And you have filters where that roll-off is relatively smooth, or you have roll-offs that are very steep. This vertical line here is the amplitude of the signal. So the level. So if I would, for instance, go from 1 kHz to, this is more or less 2 kHz, so let's say that the frequency that we have here, which is the cut-off frequency, that is 2 kHz. I can then go to a point, for instance, 4 kHz. Let's say that this is 4K here. And I can look at the difference in level here. I could measure that if I want to. Now let's say that I measure here a difference of 12 dB. That would mean that I have a roll-off of minus 12 dB per octave. Because I'm going from 2 kHz to 4 kHz, which is an octave, and I find a level difference of 12 dB. That's a very modest filter still. You have filters that are even more modest. You have filters with a roll-off of 6 dB. You have filters with a roll-off of 24 dB. You have roll-offs of even 36 dB. So that's a very strong filter. There is a side effect of a strong roll-off, which is resonance. So what does that mean? It means that the steeper this line is, the more you will get a bump on the cutoff frequency. And this bump is very effective in synthesizer technique. Yeah. So this is why in synthesizers a filter with a very strong roll-off is something that people find expressive. Yeah. And the reason is that when you move the filter while you have a sound, you do not only hear the difference in cutoff frequency, but you hear the resonance moving through the spectrum. And this resonance that is moving is something that sounds very attractive. Think, for instance, of a wah-wah pedal for a guitar player. Yeah? This is a filter with a very strong resonance, and this is why it is so expressive. Okay, now let's demonstrate first this filter before we go to the next example. The filters that I'm going to use to demonstrate these basic filter characteristics are very old analog filters from a company called Allison. You see them here. They are from the end of the 1950s, maybe early 60s, but I think already end of the 50s. They are completely passive also, which means that these filters work even when they don't have any power supply. Yeah? Now you find these filters on the patch bay in BEA5 here. You see LPF1 and LPF2 and HPF1 and HPS2, which we're going to discuss in a minute. To demonstrate the effect of the filters, I'm going to send a noise signal in them. Now, a filter can of course be used for any kind of sound, not only just for noise, but noise is very convenient when you want to demonstrate a filter, because it is a signal with a very broad spectrum. There is white noise. White noise is a signal that has all the frequencies in the audible range at an equal level. And there is pink noise, which is slightly different from white noise in the sense that the lower frequencies are stronger to compensate for the sensitivity of the human ear. So I'm going to use pink noise for my demonstration. There is no pink noise, well there is a pink noise generator in the studio, but you can't find it because it is just some PCB somewhere. But there is a pink noise signal on the patch bay which we can use. So I'm taking it from here and I'm sending it into a low pass filter. And now I'm taking the output of the low pass filter and I'm bringing it to the input on the mixing desk. Okay. If you don't know how this mixing desk works, go to the previous instruction film. I'm opening channel 1 here from the mono channel section. So the mixer input on the patch bay, number 1, corresponds to the first mono fader on the desk, and it's on the right input selector. I see already that there's a signal here on the LED. I can increase it a little bit. I open the fader, I send the signal to left and right. I open the left and the right master fader, and I open the volume control. So we hear my pink noise signal. So we have a switch here which sets the cutoff frequency, which is now at 9600 Hertz. If I move the switch, it's very audible that the high frequencies are gradually disappearing in steps of octaves. So 9600, 4800, 2400, 1200, 600, 300. So these are steps in octaves, and then here I have a dial with which I can gradually move that frequency. So I can actually multiply it until I'm at multiplying by 2, which actually means the next step. Now you can hear that this is a filter with a quite relatively strong roll-off, because the resonance moving through the spectrum is very audible. The next filter that I'm going to describe is the opposite of a low pass filter, and it is a high pass filter. So instead of this, it's now this. Everything that I said about the low pass filter is true for the high pass filter, except from the difference in the frequency range, of course. So here we have the high part passing and the low part is taken away, and here it's the opposite. But for the rest, the cutoff frequency, the resonance, the roll-off, how you describe that, it's all identical. So let's listen to a high pass filter. So instead of the noise signal going to the low pass filter, I'm now going to plug it into the high pass filter, and I'm taking the output of the high pass filter to the desk. So now I'm starting at the opposite of the frequency range, which is I'm starting at 75 Hertz, and I'm gradually going to bring up the cutoff frequency. And you can hear that the noise is getting thinner and thinner because I'm only passing through the highest part of the frequency range, and the lowest part is now taken away. And of course I still have here also this dial which I can fine-tune the frequency that I'm setting here in steps of an octave. The next filter I'm going to show is a band pass filter. A band pass filter is basically a combination of a low pass filter and a high pass filter, because what I have here now is this. So there is a low part which is taken away, there is a middle part which is passed through, and there is a high part taken away. And that's a BEA5, band pass filter. Now, I have band pass filters in the studio, but first I'm going to make one by combining a low pass filter and a high pass filter. So it's very easy. I can take the noise, send it to one filter first. Doesn't matter in which order. And then I'm going to the mixing desk. So this is also a first diagram, a patching diagram, where I use a box of 2 units on the grid of the paper here for one device, because it only has one input and one output. If I would have a device with more inputs, I would draw a larger box here, but like this is fine. And this is a symbol for a fader, and this is a symbol for a sound. Let's go to the patch bay and make that patch. So again, the pink noise going to the low pass filter. Now I'm going to take this plug and put it in the back of this one, so that the signal also goes to the high pass filter. And now I'm going to bring the output to a fader here, and I'm going to bring this output to another fader. This is not allowed, just to be clear. So you can take an output from a device and bring it to 2 inputs, but you cannot combine 2 outputs by just plugging the plugs together. You need then to mix those signals. So when those signals are audio signals, you mix them on the mixing desk. When those signals are control voltages, you mix them with a mixing amplifier, but that's another subject. So as you can see on the mixing desk, we now have signal on 2 faders. Here I have this. Here I have that. So I have a high part. This is the output of the low pass filter. This is the output of the high pass filter. And together, it's a band reject. So by moving the high pass filter frequency up and the low pass filter frequency down, like that, I'm creating a larger gap of the band reject. Yeah, so now only the high frequencies above 48 are passed through, 4800s, and only the low frequencies below 300 Hz are passed through. So there is an incredibly large gap in between those two. So a band pass becomes more effective when the two frequencies approach each other. A band reject becomes more effective when they are further apart. There is a filter in the studio, actually there are two, from a Dutch synthesizer company called Synthon. It's a kind of cult brand, in the sense that it existed in the 70s and possibly also in the 80s, and then it disappeared, and then they had some reruns of certain synthesizers that they have built. There are modular systems, there are all-in-one synthesizers with a keyboard, and then they have also been making these kind of modular filters, and this is, for instance, a Synthon phaser. Now, the Synthon filter that we see here, the 917, can do all those frequency characteristics that I have been describing. So low pass, high pass, band pass and notch. But first I need to connect it. So I'm going to the patch bay. Again, I'm going to send pink noise, and I'm going to send it into the Synthon filter and then to the output. The Synthon filter has actually two inputs, but one of them is a voltage control input, which we're not going to discuss now. We're just going to discuss the filter in manual operation. So the in is for the audio signal. The output goes to the desk, and now we are going to the filter. So the switch here now is in the position band pass. Yeah? That means that I have a band pass around the frequency that is set here with this knob. It's 500 Hz. I can move it up, I can move it down, and I can also have a kind of fine control over that frequency. With the resonance, which is the same as the roll-off, as I have discussed before, I can emphasize the peak of the band pass. Now you can already tell that this is much more convenient than having two filters where there are two settings that you have to move simultaneously. Now I just have one knob for the center frequency of the band pass. This resonance can be brought up so far that the cutoff frequency becomes audible as a pitch. Yeah? So the resonance has been brought up so far now that the filter goes into self-oscillation, which is usually something you want to avoid, but maybe as a sound effect it could be used. If I go to the other setting of the switch here, which is notch, so remember notch is the same as band reject. If the notch potentiometer is in the center position, I indeed have a notch filter. So I can move the notch frequency around, and again, now the filter becomes stronger when I reduce the resonance, because now the gap becomes larger. If I move the switch from band pass to notch, I now have a notch filter as long as this potentiometer is exactly in the middle position where it says notch, so at 0. I can now move the notch frequency, but as I said before, with a notch filter, the effect actually becomes stronger when the resonance is lower. So now I reduce the resonance and therefore the gap is wider. And the effect of the notch filter is indeed stronger. If I move the potentiometer for notch to the left, I take away the high part, so I'm left with the low pass only. And when I move this notch switch knob to high pass, I have a high pass filter. The filter that you see here is a famous filter from Sonology. It's a Brühl and Kjaer third octave filter, but it is modified by the Institute in the 1970s in such a way that you actually do not recognize the original brand anymore. The filter is behind this interface. It looks an original Brühl and Kjaer third octave filter like a 1610 or a 1612 or a 1613. Looks similar to the Brühl and Kjaer devices that we have there. So they have this beautiful mint green front panel with the black knobs, and the third octave filter would also have such a big dial. So it is basically, it consists of a series of bandpass filters where the center frequency of the bandpasses are in a distance of 1/3 of an octave. So that means that you have a very long row of third octave bandpasses, about 29. And to go through the whole frequency range, the switch sets which filter you use, so where the input signal and the output signals are connected to, but you can only use one at a time. And already in the 1950s, I'm talking about the period 1957-1960, there was a filter like that which was modified at the studio of the Delft University of Technology, and they said, okay, it's a pity that we can't use all those filters simultaneously, so why don't we modify it in such a way that we can send the signal to all the inputs of the band passes and then mix the outputs. Yeah? So if we now go to the matrix of the interface that Sonology built for this device in the 70s, we see more or less this. So we have here the band passes, indeed at a third of an octave distance, in a range between 25 Hz and 16 kHz. There's an input matrix and there is an output matrix. Now if we go to the patch bay, I start first with connecting the pink noise to input 1 of the third octave filter. You see here input 1 on the input matrix. This is by far the most common way to use this filter, which is to send the signal that is connected to input 1 to all the bandpass filters in the device that is inside. And I'm doing that at an equal level, so the signal goes at 0 decibels to all the bandpass filters. I could make a kind of curve if I wanted to. So for instance, this would mean that now the signal that goes to the bandpass filter with a center frequency of 1 kHz is at -9 decibels compared to the others. Yeah. But usually this is far better. Then here we have an output selector. Yeah. On the output selector I can define where the output of one or more of these band passes is going. So I can say, for instance, let's take the output of the filter 1 kHz to direct output number 2. These 10 go over these 10 potentiometers. I will discuss that later. So now I'm going to use a direct output. So back to the patch bay. I'm taking direct output number 2 from the third octave filter, sending it to the desk. And I hear a beautiful sound, which is a very narrow bandpass. Yeah? This is so narrow because the third of an octave bandpass is very small, very narrow. And then, of course, the next band is a third of an octave up, like that. And as I said, I can make combinations. So I'm now going to draw a wider diagram, again with 1K here, 16 kilohertz here, and what was it, 25, the lowest one here. So this would be more or less the 1/3 of an octave around 1 kilohertz from the Blue and Chiar filter. The fact that we can combine all those outputs again into one signal could lead you to the idea that that would then recreate the original input, because you are having all the frequency ranges back again. But that is not true. Why is that not true? Because the next third of an octave bandpass might be here, the center frequency, but the frequency itself, the output itself, would look like this. So you basically are getting this. So not only will you start to notice all those resonances, but here in these areas where the filters overlap, you get all kinds of crazy stuff. Phase cancellations, and so on. And this is why I said that it's such a famous filter, because the sound that you get when you send the noise into this filter and you combine the outputs is something that you might hear in many pieces that have been made in the analog studio in the 70s at Sonology in Utrecht. So let's try that out. Okay, up to 50 is enough. Now, this is of course far from similar to the original noise signal, because if you listen carefully and if you have a musically trained ear, you notice a kind of augmented third chord in it. Because you go up a major third and another major third, and then you are at the octave again. And as I said, this is the result of the phase cancellations that occur in the areas where the filter bands overlap. Now, to make that effect even stronger, I can take the pink noise and also bring it to the mixing desk directly. In the desk I have my unfiltered pink noise, and I have the filtered pink noise. If I combine them, I will increase the effect of the phase cancellations. So listen carefully what happens. I can change the phase here on one of the channels. One thing I forgot to mention about the cutoff frequency and the strong roll-off, one of the reasons why it is also called resonance is that it not only has an effect on the frequency characteristic of the sound that you hear, but it also has an effect in time. What do I mean by that? If you hit the skin of a drum, for instance a timpani, you hear a specific sound and you give a very short impulse, and after that the skin resonates, and that resonation has a very specific frequency characteristic, which is why we recognize a pitch in the resonance of a timpani. So everything that I hit has a different sound because it has a different resonance frequency pattern. Filters do also resonate, which is not directly audible when I use noise as an input, but when I use an impulse as an input, I will very clearly hear that. So let's try that. So to demonstrate the resonance effect, I'm going to use the Synthon filter again, which is the filter that I could bring into self-oscillation by increasing the resonance with the knob on the device. Yeah, so now I'm not going to use noise, but I'm going to use an impulse. And I'm going to take that pulse from a function generator. So this function generator I'm going to put in a very low range, so not in the range where it produces audible signals, but where it produces very slow signals. And I'm going to use the block internal low frequency. So I can let you hear how that sounds by bringing it to the fader. Okay, so I'm going to open the fader. So this is an unfiltered square wave. You already hear a resonance, which is actually the resonance from the loudspeakers, yeah, because loudspeakers are filters. You think that loudspeakers are neutral, but they are far from that, of course. So the pulse that you just heard from the square wave is now going into the Synthon filter. The output of the Synthon filter is going to the fader again. And we now hear the same pulse, but filtered. And I can control the pitch, if you want to call it that, with the bandpass frequency. If I now increase the resonance, it indeed starts to sound like a drum. And now we hear the resonance of the whole rack of equipment. So what would happen if I sent this pulse now to the Brüel filter that we were just using, so the third octave filter. So I'm going to take the noise away. And I'm going to use the block output from the function generator as an input for the third octave filter. So here I have the unfiltered square wave again. And this is the output of the filter. So you can, yeah, maybe it's not so easy to hear on the instruction movie, but what you hear is a kind of very interesting resonance curve after the pulse, in which all the individual filters have different resonance times. So it sounds like a kind of sweep. Now I'm combining again the out of phase original with the filtered sound. So that was it for this second instruction video. Again, if you do not know yet how the mixing desk works, then go back to the first instruction video and more will come.